Welcome to today's lesson, Analysis of the Common Emitter CE Amplifier with an Emitter Resistor. We will be using the H-parameter model to work through this circuit's behavior, including its current gain, voltage gain, input resistance, and output resistance, and we will finish with a full worked example. Before we get into the mathematics, let's look at the big picture. This table compares three versions of the common emitter amplifier: one without an emitter resistor Re, one with an unbypassed Re, and one with Re plus a bypass capacitor Ce. Look first at Q point stability. Without Re, stability is poor. The operating point drifts easily with temperature and component tolerance. Add Re and stability becomes excellent because Re introduces negative feedback that holds the Q point steady. That excellent stability is preserved even when we add the bypass capacitor, because the capacitor only affects the AC signal, not the DC bias point. Next, voltage gain. Without Re, gain is high but unstable. It depends heavily on HFE, which varies from transistor to transistor. With an unbypassed Re, gain drops but becomes stable and predictable. Add the bypass capacitor and high gain is restored for a C signals because the capacitor shorts out Re at signal frequencies while DC bias stability is unaffected. Distortion follows the same pattern. It's higher without Re, lower with Re, and higher again once the bypass capacitor removes that feedback for a C. Input impedance is lower without Re, calculated as beta times Re prime. Adding an unbypassed Re raises input impedance since it becomes beta times the quantity Re prime plus Re. With the bypass capacitor added, input impedance falls back to its lower value because Re is once again shorted out for a C. Finally, in terms of extra components, the unbypassed version needs just one resistor, while the bypassed version needs that resistor plus one capacitor. Keep this table in mind. It's the roadmap for everything we derive on the following slides. Here's the circuit we'll analyze: a common emitter amplifier with an unbypassed emitter resistor Re biased using R1 and R2 with coupling capacitors C1 and C2. On the right, you can see its small signal equivalent circuit built from the approximate H-parameter model. We neglect HRE and HOE here because both are numerically negligible, and dropping them keeps the analysis much simpler without any meaningful loss of accuracy. Let's start with current gain. AI, since all the collector current IC flows out as IO and IC equals negative HFE times IB, our current gain AI equal to IO over IB is simply negative HFE. Now for input resistance, Ri, applying Kirchhoff's voltage law around the base loop, VB equals HIE times IB plus the quantity 1 plus HFE times IB times Re. Dividing VB by IB gives us Ri equals HIE plus the quantity 1 plus HFE times Re. Notice what this tells us. Adding Re increases input resistance by a factor of 1 plus HFE times Re. This is one of the defining features of adding an emitter resistor. Now, why does input resistance matter so much in practice? Think of any real signal source as having its own internal source resistance. Rs, a microphone, a sensor, and so on all have some non-zero output resistance. When you connect that source to your amplifier's input, you form a voltage divider. V in equals Vs times Z in divided by the quantity Z in plus Rs. If Z in is much greater than Rs, that fraction approaches 1, meaning almost the entire source voltage reaches the amplifier input with negligible loss. But if Z in is comparable to or smaller than Rs, a significant chunk of the signal voltage is dropped across Rs itself and never even makes it into your amplifier. That's signal loss before amplification even begins. This is exactly why the higher input resistance we get from adding Re is so valuable. Continuing with the same equivalent circuit, let's derive the voltage gain AV. We know AV equals AI times RC divided by RI, which expands to negative HFE times RC divided by the quantity HIE plus 1 plus HFE times RE. In most practical designs, the quantity 1 plus HFE times RE is far larger than HIE, and HFE itself is much greater than 1. Under these conditions, the expression simplifies neatly. AV approximately equals negative HFERC over HFERE, and the HFE terms cancel, leaving AV equals negative RC over RE. This is a powerful result. The voltage gain of this circuit can be seen to be independent of the device parameters. It depends only on the ratio of two resistors you choose, RC and RE, which makes the design far more predictable and repeatable across different transistors. Now let's look at output impedance, RO and RO prime. RO is infinite because neglecting HOE leaves an ideal current source as the only output side element. And with Vs set to 0, as we do for any Thevenin resistance calculation, the base current IB is forced to 0 regardless of the test voltage we apply. So the source supplies no current under any output voltage, which is exactly the definition of an open circuit, or R equals infinity. Since RO is infinite, when we place RC in parallel with it to get the effective output resistance, RO prime, the infinite resistance simply drops out. RO prime equals RO in parallel with RC, which equals RC. Let's put all of this into practice with a worked example. We need to compute the overall current gain AI equal to IO over IS, the overall voltage gain with respect to the source AVS equal to VO over VS, the input resistance RI, and the effective output resistance RO prime for the amplifier shown. Here are our transistor parameters. HIE equals 4 kilo ohms, HFE equals 200, and both HRE and HOE are taken as 0. The circuit itself has a 5 kilo ohm source resistance RS, bias resistors R1 at 90 kilo ohms and R2 at 10 kilo ohms, a collector resistor RC of 5 kilo ohms, and an emitter resistor RE of 1 kilo ohm. Let's begin with the easiest quantity, the current gain measured with respect to base current rather than source current, since AI prime equals IO over IB and that ratio is simply negative HFE, we get AI prime equals negative 200 straight away. We'll build on this result over the next two slides to find the overall gains reference to the source. Now let's work through the full solution. First, the input resistance at the base Ri equals HIE plus the quantity 1 plus HFE times Re, substituting our values 4 kilo ohms plus 201 times 1 kilo ohm gives us Ri equals 205 kilo ohms. Next, we need the effective input resistance seen by the source, which also accounts for the bias resistors. First, we combine R1 and R2, 90 kilo ohms in parallel with 10 kilo ohms, which we'll call RB. That parallel combination works out to 9 kilo ohms. RB then combines in parallel with Ri to give us the effective input resistance 9 kilo ohms in parallel with 205 kilo ohms, which comes to 8.62 kilo ohms. Now for the overall current gain AI equal to IO over IS, we break this into two ratios, IO over IB times IB over IS. The first ratio is just negative HFE. The second ratio, IB over IS, comes from the current divider formed by RB and Ri, giving us RB over the quantity RB plus Ri. Multiplying these together, negative 200 times 9 over the quantity 9 plus 205 gives us an overall current gain of negative 8.41. Finally, the overall voltage gain with respect to the source AVS equal to VO over VS. We split this into two ratios, VO over VB times VB over VS. The first ratio works out to AI prime times RC over Ri. The second ratio is a voltage divider between the source resistance and the effective input resistance, RIFE over the quantity RS plus RIF. Substituting our numbers, negative 200 times 5 over 205 times 8.62 over the quantity 5 plus 8.62 gives us an overall voltage gain of negative 3.09. To finish, let's confirm the output resistance for this specific example. As before, RO is infinite because neglecting HOE leaves an ideal current source as the only output element. And with Vs set to 0 for the Thevenin resistance calculation, the base current IB is forced to 0 regardless of the test voltage. So the source supplies no current under any output voltage, which is the definition of an open circuit. Therefore, the effective output resistance RO prime equals RO in parallel with RC, which is infinity in parallel with 5 kilo ohms, and that combination simply equals RC. So RO prime equals 5 kilo ohms. That completes our full analysis of the common emitter amplifier with an emitter resistor. We've derived its current gain, voltage gain, input resistance and output resistance from first principles and confirmed every result with a numerical example. Thank you.